Hey, what's up everyone? So on to our next bit of videos where we are going to look at population sizes and how and why they vary and some of the questions that population ecologists will ask. And then we're going to focus this idea onto the wolves of Yellowstone and kind of see the down the line repercussions of populations of this individual, as I mentioned in the previous video. So let's get started. So there are 5 main questions that population ecologists will ask basically themselves, or it'll be their scientific questions, if you will. So how many individuals are within one population? And what is happening to those numbers of that population? Are they increasing? Are they decreasing? Or are they staying the same? Additionally, what is their pattern of reproduction? So is it just a straight up offshoot? Is there something that limits those patterns? What's going on here? And then these last 2 questions, population ecologists do often ask. However, we are not really going to touch into these ideas in this particular class. But these are questions that are actually coming up a bit more in some current event things and what some folks are asking around the world and things like that, but we're not going to touch into that in our lessons here. But those include what is the pattern of mortality, and more importantly, what's the age structure of that population. So we're going to address this first question here, looking at how many are in the population and how in the heck do scientists count these things? There's many different methods and different strategies that folks use. I'm not too privy to every single one of the ones that people use, but you can use things like tagging or using drones or using the knowledge of their population growth of a certain area to kind of estimate that. Perhaps you've heard about the billions of crabs that just disappeared in the Gulf of Alaska. That's from not being able to monitor where those crabs are now, but also knowing their population growth and their breeding schedules, if you will. So that was how they were able to measure billions of crabs. But something that we also consider is the minimal viable population, or the MVP. Not the fun way to measure MVP. But going back to that last point also, it is kind of hard for different species, right? Because, some are nocturnal, some are underground, marine species are moving around all the time. So there's various different surveying techniques that we use to try to calculate these accurate numbers. In Yellowstone, ecologists introduced members of a nearby population to help growth, right? Because we were like, oh gosh, the wolves are gone. That's not very good. So we reintroduced a population from somewhere else in order to help boost local populations. But another way that ecologists used this idea was through the California condor captive breeding program. Crazily enough, the California condor, this beautiful bird you see here in this picture, the populations dwindled to a meager 22 individuals spread out around California, which is, of course, below the MVP, below the minimal viable population, with numbers that were dropping. So wildlife managers did something super drastic where they captured all of the individuals, and we're trying to breed them, get them to breed with each other. And they didn't have any other populations to bring in. We didn't have a nearby population, say, of, the Canada condors, so they had to use something really, really drastic in order to manage the population of California condors in particular. The next thing that ecologists consider is population density. It's not just enough to know how many folks are in one, or how many of an individual are in one area. We also need to know how densely they're packed in, which means the number of individuals per unit area or volume. Something that you can consider, and perhaps something you're familiar with, is of course the population of California. The The San Francisco in particular is so densely packed, with the Bay Area also as well is just super densely populated. There's millions of people here in the Bay Area. Whereas if you go, say, into the state of Nevada, it's incredibly spread out, right? Where it's densely populated in little pockets, right? You got Reno and you got Vegas, and that's kind of about it. Or just considering the East Coast of the United States versus the West Coast of the United States. If you look at population maps, the East Coast is way more densely populated than the West Coast, in kind of like this overall whole situation. So we know that if populations are too low, then it's going to be really difficult to find mates. And if it's too difficult to find mates, that's going to lead to more inbreeding and a less healthy population. An example that I have is that I have two of my cats. They are brother and sister, but their parents were also brother and sister, and so this has led to some genetic mishaps, if you will. They both have broken tails, and one of them is very fat and the other one is very skinny. So we believe that that has come from lots of inbreeding down the line. You could also think of things like different breeds of dogs and different health issues that they have. I love me some pugs, but their poor face just leads to a lot of issues. Anyway, also if a population is too high, then that means that this can lead to increased predation, higher competition, and faster spread of disease. These are also density-dependent factors, right? Which is pretty interesting. Also, distribution has a pretty large impact here as well. So these are the three main patterns that are observed. So what do you think drives this distribution? Which do you think would be the most or least common? And how would you describe how humans in California are distributed? So check out these three distribution patterns that we see. We see clumped patterns, maybe more random distribution patterns, perhaps that of flowers, and maybe more uniform distribution patterns, like you would see maybe in the desert Southwest. It's pretty interesting, right? So how do you think that humans in California are distributed? Are we more clumped, random, or uniform? What do you think? Take a moment and consider those ideas. The next question that we want to address is, how do populations change in size? Are they increasing or are they decreasing? So we're going to use a little bit of math in order to help us address these questions. On a global scale, if we were considering a closed system where really we don't have really humans coming into Earth, immigration would not be an issue here, or like aliens coming in and humans leaving, in a sense it's a closed system, right? So the birth rate, or the rate of human population, is birth rate minus the death rate, which is relatively steady, or can be relatively steady. But on a more local scale, can be more of an open system, right? Where you can consider immigration and you can also consider emigration. So folks coming in and folks leaving, right? So the rate then of the population size has to take these two things into consideration as well. So not just how many people are being birthed versus how many people are dying, we also have to take into account how many folks are coming in and how many folks are leaving. Scientists can also look at different points in time when we're considering populations of animals. In particular, in this example, in 2009 to 2010, scientists noticed that the wolf population increased from a value of 320 wolves to 343 wolves, which resulted in a growth rate of about 7.2%. Your book goes into how to do this calculation, but I will walk us through this as well. I know that math can be pretty scary for a lot of us, so I'll walk us through. So what we do is we take the amount of population in the second time period we're considering, and the initial population. So in this case, we're going 443 minus 320. 343 minus 320, which equals 23 wolves. So then you take that amount of growth and divide it by the initial rate, the initial population. So in this case is 23 divided by 320 times 100%, and that gives us about, you round it up to about 7.2% growth increase. But there's got to be limits to these growths, right? So there is, this is from your book here, looking at the exponential growth, and this can occur where no limits exist within the growth, which is common when a species enters a new environment, or there can be an influx of new resources, or there can be a loss of predators. And this is what happened with the elk population in Yellowstone. The elk population doubled from 1914 to 1932 when the predator program was allowed folks to hunt wolves to basic near extinction. But we also know that there can be environmental resistance within this idea as well. Exponential growth cannot last forever. It just mathematically cannot exist that way. So as a population fills its environment, the growth rate will decrease, right? So as it fills its environment, the growth rate will eventually decrease. And once some of these resistance factors kick in, like predators, competition, disease, then that can slow down the growth rate, causing our exponential J curve to then curve to the transition into this more S curve sort of idea, where we kind of level out at this carrying capacity, which we denote as the value K. This is the maximum population size that a particular environment can support indefinitely. And this value can actually increase or decrease over time. Again, this will depend on the environment itself. So this is something that we would see just in general. Last idea that I would like to cover on this topic would be density dependence. So there's basically two categories that we can break dependence into, being density dependent, where factors whose effect on population changes as the population density changes. So that can be through competition, through disease, and through predators, right? If you just have too many people, like that's going to be too much competition. You might want to wipe some of them out. Or disease can wipe whole populations out, right? We've just lived through a pandemic, for goodness sake. But also predators, right? Predators can take folks out as well. Whereas density independent ideas give way to the fact that the effect on population growth is not influenced by population density. So this is more like natural disaster sort of things. So things like fires, floods, and avalanches and other natural disasters. So you can think of density dependent as like just what happens within that population in particular, and independent thinking of things like natural disasters. So did Mother Nature being very angry, did this make a population decrease, or was it factors within the population itself that made the population decrease? So I hope that this video has been helpful, or these several videos have been helpful in terms of understanding these first several questions of population ecologists and the questions that they ask. Thank you very much for watching.